Okay, thanks for sticking around. I hope to make it worth your while. My name is John Kooker, and I built the OptiActor for iPad. And as Professor Das mentioned, I've been working with the Calit-2 Visualization lab, Drs. Kai and Falko. Quick background. So today we're going to go through a quick background, which will have some overlap with our previous presentation. So I'll go quickly through that, talk about my statement of work, and then how I actually approached making this application. I should talk about how the application works, the modes of operation, some conclusion, and then we'll go downstairs for a demo. So let's start with some background. CGLX in hyperspace. Hyperspace stands for, as you know, highly interactive parallelized display space. So that's the wall that's in the second floor of Calit-2. That's the wall downstairs below. Over in Atkinson Hall, it's the world's highest resolution display at 286 million pixels. So it utilizes the middleware. It's called CGLX. Which is cross-platform cluster graphic library. It's based on OpenGL, and it includes APIs for external control like mouse and keyboard, also multi-touch, and we'll get into that. The iPad was just released this quarter, and it's been a huge success, and it's sort of sweeping the nation and the world now. 2 million units sold. Important pieces of the iPad that we're going to use are its Wi-Fi. It's capacitive multi-touch display as opposed to refractive optical, and a hardware accelerometer. In order to develop software for the iPad, you need to use Apple hardware, Apple software. It's all one big ecosystem. So Apple's SDK includes an integrated development environment called Xcode, Kooker frameworks, which they provide for software development, and it's written in the Objective-C programming language, which is new for a lot of people. It also supports C++, which CGLX is written in, and so my app is a fusion of those compiled as Objective-C++. In order to put any code on an actual device, iPod, iPhone, iPad, you have to be part of the iPhone developer program, and that costs money. Unless you're in a university program, which we partnered with a team over in the CSE department with Professor Gupta. We were able to get up and running real quick this quarter. And be able to create certificates and provisioning and register developers, register devices, get the apps all running because Apple's locked down their system really well. They highly value the security of their system. So the statement of work is basically we're making an app for the iPad that incorporates a CGLX network library for communication, allows you to use the iPad for mouse and keyboard input emulation, as well as multi-touch and accelerometer. And then the idea was to conduct user testing on hyperspace installations in Atkinson Hall, Jacobs Hall. That went very well. And then based on feedback from this user testing, which we began really early and was a key part of our my work. Based on that feedback, I defined and executed some stretch goals for the remote interface. So this is the block diagram. So on the iPad, we've got the OptiActor application, which utilizes the CGLX network library. That communicates over Wi-Fi to a Linux host running the CGLX head node, and that head node commands these render nodes for drawing. So it's a simple block diagram. Oh, and also key was that getting this network library built on iPad was very tricky. Apple has very specific guidelines about not allowing dynamically linked libraries, only allowing static libraries, and how you can build build software into your applications. I'll talk a little bit about touch processing modes. So there are two mouse emulation modes. I call them trackpad and absolute. So on the iPad, if you so the trackpad is the most natural one, and in user testing we found that this was the mode that everyone just sort of naturally gravitated to because they had this touch interface in front of them. They started shoving the cursor around. So the trackpad works just like that, just like your laptop. Absolute positioning is also kind of nice because then you can touch one corner and the other corner and instantly move the mouse from one end of the screen to the other end of the screen. So depending on the apps that you're using, because again, the design is that this application would support as many existing CGLX hyperspace applications as possible. I also included mouse buttons for two-handed operations. So you click a button and click a mouse button and move with your other hand, and you can also use two fingers for mouse wheel scrolling. Multi-touch is where it gets really exciting. The iPad supports up to 11 simultaneous touch points. As I noted in class, I verified that with 10 fingers and a nose. It makes for very natural interaction with photo applications where you're shoving pictures around and zooming, paint applications as you're finger painting like we did in kindergarten. There are two modes for this. There's one that's event-driven, and it only sends changes as multi-touch parameters are changed, and that, of course, requires less network bandwidth. However, there were some so the existing multi-touch applications were designed for a multi-touch table that the folks in the Gravity Lab had designed, and that table sends data at 60 hertz. And so some of the applications had that, were assuming that the data would come in at that rate and needed that for animation. So I included a constant rate mode to support those, because again, we want to support as many apps as possible. Keyboard and accelerometer, really briefly. I designed it so that the keyboard can be on screen and you can still use the mouse, and so you can interact as easily as possible. Accelerometer can be switched on and off depending on whether you're actually using it, because right now, since adding accelerometer data is brand new, there aren't applications that support it just yet, but OptiActor is ready for it. A stretch goal that I defined near the end of the quarter was realizing that when you have your iPad, you stand in front of the wall. In order to actually use it with the wall, you have to get the IP address of the iPad, then go over to the Linux PC, type in that IP address, because the iPad is a passive server. It starts the server and waits for the head node to connect. So that isn't a great use case, not a good user story. So the better scenario is to create active servers where the iPad, you know the IP addresses of your head nodes, your applications. You enter them here, request a connection from the head node, and then the head node will connect and disconnect as you ask for it. So that way you can command these applications entirely from the iPad. Works really well. In conclusion, we created a new intuitive interface for the Hyperspace OptiPortal system. It supports a majority of existing applications in engaging a new interaction paradigm. Supports mouse and keyboard, multi-touch, and accelerometer, and it's self-contained on the iPad. It doesn't require any new helper processes on the head node. It works, as we're about to see, just walking up downstairs. Also, all the source code is freely available on GitHub, which uses the source control system Git, so it's really easy for other people to pick up where I left off, branch, merge, do whatever they like. So if you'd come with me downstairs, we'll take a look.